The last time we were doing this problem about comparing two proportions. And when we did this, we did a one-tail test. We did the Z, we did our pooled proportion, our combined proportion. We got a Z score, and we said reject the ID. We also looked up the p-value, and again, it said reject the null hypothesis. And the null hypothesis was that the one gas station had a lower thing than the other. And then we did a confidence interval for those proportions. And when we did the confidence interval, I said that tests and confidence intervals like flip side to each other. And if I see 0 in my confidence interval, it means I should accept the null hypothesis. And then I said, well, let's do a confidence interval for the problem we just did. See a problem? 0's in my confidence interval. That means I should accept the null hypothesis. But this result said rejected. Why? I forgot something. It's not a huge thing, but I did forget that confidence intervals are two-tailed. And a two-tailed test has a different Z value than a one-tailed test. One-tailed tests are smaller Z values than two-tailed tests. So this confidence interval is automatically a two-tailed test. And that's why this gets accept the null, and my Z test, which was a one-tailed test, gave me reject the null. So it's important to remember this subtle but necessary difference. When I am doing a confidence interval, I'm really looking at a two-tail idea. Questions? I literally thought of that as everybody was walking out the door. I'm like, I wonder why that worked differently in two different. Oh, okay. In doing that problem, we made an assumption because we used a pooled proportion. In doing our Z tests for paired samples and for unpaired samples, we asked, could we make the assumption that the variance, the standard deviation, was equal? I want to test that. If I have a smaller variance, I get clustered together data. And that means less variation, more consistency in my outcome. I talked about variation as like target shooting. And I said you could have a big variation and spread out your target, your shots on target. You'd have a very small variation of a tight cluster. Even if you miss, you can then correct your aim and your clustering will stay tight. Small volatility in asset returns, quality control behaviors. These are things that I would like variation to be smaller, and so I want to control that and test for it the same way. So again, I need a null and an alternate hypothesis. And I'm going to check variance 1 against variance 2. Variances are squared, standard deviations aren't. So my null hypothesis and my alternate hypothesis are going to follow the same sort of pattern. Hey, look, the alternate hypothesis shows sigma 1 smaller than sigma 2. So this is a left tail. This is a two-tail because it's equal or not equal. My alternate hypothesis shows sigma 1 bigger than sigma 2, so we're looking off to the right side. Now, I must tell you that this bothers me quite a bit. Because which one you call sigma 1 and which one you call sigma 2 changes whether you're doing a right tail or a left tail. And I'd rather have a single comparison behavior. So most of the time, instead of comparing these to each other, I take the ratio of them. If I take that, and instead of just looking at sigma 1 versus sigma 2, I look at sigma 1 over sigma 2 squared, well, then I could rewrite these and compare them to 1 every time. And now I see, oh, less than 1 is left, bigger than 1 is right, equal or not equal is the two tail. You'll see both of these used interchangeably for the most part. I have a slight preference for the bottom one, but it is really very slight. So if those are my hypotheses, I need to then ask, what's the statistic I'm going to test? And what's my critical value worked out here? So my test statistic is an F, not a Z, not a T. This is named after Ronald Fisher, who's the person who developed this test. And all we do is we take the ratio of the actual calculated standard deviations. I need to use the samples, not the population one. My apologies. But Fisher decided that this really needed to take into account both sample sizes. And so this test statistic doesn't have a degree of freedom. It has 2 degrees of freedom. And Fisher, after doing a number of experiments, deduced that this distribution didn't look normal. It didn't look uniform. This distribution looks different. So our distribution now for this setup is very different looking. Same picture. The picture of the F distribution Looks like that. The long tail going off to the right, there's this big bump down here towards the middle. And then you'll notice these numbers are always positive. S1 squared over S2 squared, those are always positive numbers. If I take a fraction, top is positive, bottom is positive, result's positive. So this is always bounded on the left by 0. It's very high peak close to 0, and then it tails off going off to infinity to the right. This distribution looks very different. And it's a 2-parameter family, so it depends on my distribution degrees of freedom. How many people are in the first group? How many people are in the second group when I'm comparing variance? Which means I have a crap ton of tables for this. And the table depends on 3 different things. What's the alpha I'm picking? And what are the degrees of freedom? That means in our textbook, we actually have several pages of F tables. I hope it's to no one's surprise that this is Appendix F. But Appendix F is all sorts of F tables. Now notice what they do here. They only give me the right tail in this picture. And this depends on alpha. So these are with alpha being 0.1, and then there's 2 different degrees of freedom that I need to look up to find my numbers. But here is another table where alpha is 0.05. And again, 2 degrees of freedom. And here's another table where alpha is 0.01 and 2 degrees of freedom that I need to look up. Using this table sucks. But these commands are available in Excel. These commands are available on our graphing calculators. So I can do all the work automatically, and I don't have to generate the numbers, which means 99.9% of the time, if I want to do a comparison, I'm going to do all the work in Excel. I'm just going to ask you, what does it mean? Now notice, there are 3 different tests because there are 3 different sets of hypotheses. If my null hypothesis, I'm doing a left tail test, then I'll reject when I'm in this left rejection zone. If I'm doing a 2-tail test, I reject when I'm in either the left or the right zone. I'm doing a right tail test, I'm only rejecting the right zone. And this is the one the table gives me. Okay. Problem. Left and right are different. They're related, but they're different. I find it annoying to use the table to find both values, because to get the left value from the right value, we have to do some work. Remember, when we were doing a z-test or a t-test, we had a critical value. We're going to have that same sort of critical value in our f-test, but we're going to have a right critical value, and we're going to have a left critical value, and they're different. So I don't just have f crit. I have 2 of them. Again, I will find it most often easiest to do this work in Excel. But if I'm stuck with my table, it turns out that when I do my right value, I need 3 pieces of information. I need alpha, df1, and df2. The book will write the subscripts df1 and df2, won't write alpha. So you need to know what alpha is before you even go look stuff up. How do I know where to look? In the table, it tells me which is DF1 and which is DF2. In our case, DF2 is by row and DF1 is by column. In our appendix. So, for example, I'm going to do a calculation with alpha being 0.05. I want to find FR, and I'm going to tell you right now up front that there are 11 people in group 1 and 8 people in group 2. What are my degrees of freedom? Ah. Now, if I am doing a one-tail test, regardless of whether that one tail is left or right, I want all the area in one tail. Yes? I want the rejection area to be in one side. Whether it's a left tail or a right tail, I want all of that 0.05 to be on one side. Yes? So I know I need to go to the 0.05 table. Way back here, my F table, appendix F. Point 0.05. So if I'm doing a left test or a right test, I'm going to need to use this. But notice this picture is for a right test. Degrees of freedom were 10 and 7. DF1 was 10. DF2 was 7. So by column for 1 and by row for 2, that makes this number, 3.64, my right tail number. So before I go any further, I can say, hey, wait a minute. And our book would write this as F107 on the chart for 0.05. But you'll notice 0.05 is not written there anywhere, is it? That annoys the hell out of me. And according to our chart, we got 3.64. But to get the left version, I have to do something different. I have to switch the degrees of freedom and order, and then I have to take 1 over that number. So what do I do in my chart to get that here? I've got to go to F710 rather than F107. So degrees of freedom 2 goes first. Which means now I have to treat this as if it was DF1 and this as if it was DF2. It's in the wrong order. So I go to my table, and instead of going 10, 7, I go 7, 10. And I get 3.14. And then I have to do 1 over 3.14. Now, what happens when you do 1 over 3.14? What do you get? Grab your calculators, give me a number. 0.318. Now, let me go back and look at my picture for a second. And let me actually think about this. Does that number seem reasonable? A left tail should be a number close to 0. A right tail should be a number further from 0. So this number being close to 0, that makes more sense to me. I get it. I don't like it, but I get it. However, these are for 1-tail tests. What if I'm doing a 2-tail test? What changes when I do a 2-tail test with my actual little area picture? Instead of that 5% being on one side, it's split to be on 2 sides, right? The table we were just looking at is the wrong table. Because this table, F.05, assumes that this shaded area is 5%. But if I split it to do a 2-tail, then this shaded area is not 5%, it's 2.5%. And that means instead of using this table, I need to use this table. Now, again, I'm going to tell you right now, right up front, there are the Excel commands. I want the left one, I do F inverse. I want the right one, I do F inverse dot right tail, RT. I'm going to do this in Excel 99.99% of the time because it's a lot easier. But what that means is that what I need to do is write out my hypotheses, do my calculations, and understand and interpret the answer. So, problem number 37 simply asks us, here's the summary information. Let's do this. You want to do A, B, or C? We can do more than one, but which one do you want to do first? Okay, if I do A, it says we're going to use 11 and 8, a two-tail test. Two-tail. Hey, wait a minute, 11, 8, those are the same numbers we were just looking at, right? Okay. So let me write down all of that information so that I have it in front of me. And then we can crank out some numbers here. 37A. S1 is 5.1, N1 is 11, S2 is 3.2, N2 is 8, two-tailed test. Okay, I'm doing a two-tailed test to determine whether or not the variances are equal. What's my null hypothesis? Yes, Max. Okay. So it's either the variance is the same, or I could write it as the ratio is 1. And then the alternate hypothesis is it's not. Right. But the reason I want to have this idea in front of me as well is because that's related to our F, right? F is ratio. Okay. Two-tailed test. Before I actually do this, I realize right now I'm missing something. There's a number that's not up there that I need. In the text, it needs to give me alpha. What is my confidence level for this problem? What's it say in the textbook? Because I didn't write that down. I was an idiot. Oh, it says in the root of the problem, use alpha equals 0.05 for all tests. So I'm going to put that up here. There we go. Now I have that. If I'm doing a two-tail test, I'm going to want alpha over 2. Half the area should be low, half the area should be high. So I have to remember that really I want to do 0.025. So to do the left value, I do f dot inv 0.025 df1. What's my degrees of freedom 1? Right, and degrees of freedom 2? Perfect. So I'm going to go directly to Excel, and I'm going to calculate this. Equals f dot inv parentheses probability 0.025, degree of freedom 1, 10, degree of freedom 2, 7. Notice that's number close to zero, right? That's my left side. That number should be a small positive number. What's my right side? Well, that's an F inverse right, RT. Again, the probability, 0.025. And now I'm going to give it, it says DF1, DF2. I don't have to reverse anything. I only have to do the reversal when I'm dealing with the paper table. So I can write that as 10.7 again. Great. Those are my critical numbers. Those are my critical numbers. What's my actual calculated value? What's my test number? I need to know what my test number is outside of these. We didn't actually do the test. What's the test number? According to the pieces of information on my paper, I'm going to actually write over here, FL, FR. S1 was 5.1 and S2 was 3.2. So my calculated F value would be S1 squared over S2 squared equals that number squared divided by that number squared. By the way, since you're squaring the top and squaring the bottom, you could also do it as the number divided by the number, square the whole thing. Same exact result. This tells me everything I need to know. So here's my question. Are the variances different or not? Do I reject or accept my null hypothesis?
Outside of like the 4.76.
Exactly. Our rejection area is below the left or above the right. We shade the outside for a two-tailed test. We're in the middle. We're in the white area. We're in the unshaded area in our picture. Therefore, we do not reject. Which means this sample does not show different variances. In spite of the fact the first standard deviation was 5 and the second standard deviation was 3, they're not far enough apart for me to say there's really a difference between these two behaviors. Questions? Again, given summary statistics, I can do this on my calculator. So let me walk through the same idea here. Under the stats button, that left column, sorry, right column is the tests. So I go over to the tests and way down at the bottom, there's my F test. And I'm going to put in statistics. There's my standard deviation 1 and 2 and the population sizes. And I can tell you, do I want to do a two-tailed, a left, or a right? What's your null hypothesis? Right there. Sorry, that's the alternate hypothesis, if you look carefully. That's the alternate. Am I doing two-tailed, a left tail, or a right tail? Now, when I do this, it's not going to give me the F values. What it actually gives me is a p-value. What's that p-value mean?
Means the same thing, it's a lot bigger than 0.05.
If it's bigger than 0.05, we reject. If it's smaller than 0.05, we, sorry, the other way around. If it's smaller than 0.05, we reject. If it's bigger, we don't. Hey, that's way too big. Don't reject. If you're doing a one-tailed test, same condition applies. But if I'm doing that on here, I don't need the actual F values because it gives me P. Now notice when I put in this information, nowhere in this list did it return F left and F right. It just gave me the calculated F value. And then it computed the p-value from it. I can also, in this test, put in the data if I put the data in list 1 and list 2 respectively. That's the same thing I can do in Excel, and Excel is much more powerful, so I'm going to do one like that in Excel. Here. Problem number 39. A manufacturer making drill holes in sheet metal, they're supposed to be half centimeter in diameter. We have replace a drill head. Does the new version have smaller variance than the old version? I'm not even going to do any calculations by hand at all. I just need to know where to start with my hypothesis. Looking at these two sets of data, we need to decide which is set 1, which is set 2, and then we can decide what our null and alternate hypotheses should be. So based on the way that table is written, which would you make set 1, which would you make set 2? This is literally a coin flip. Okay, if the new drill is set 1 and the old drill is set 2, I'm going to jump over to Excel and I'm going to put all this information in. Here's, that's the wrong one. That's the wrong set. share. Question 39. Here it is. Share. Here's the data. And they put the new drill on the left and the old drill on the right. So I'm perfectly happy to make it set 1 and set 2 the way we just said. I'm going to go to the data tab, go to my data analysis, and I notice there's a test right there, F test, 2 sample 4 variances. That's the test I want to do. Right there. So, okay, variable 1, there's variable 1, variable 2, there's variable 2. Yes, I put the labels on there. I get alpha being 0.05. Yes, it said that alpha equals 0.05. And I'm going to put the answer in a new page, and it does this. Please notice, gave me an F value for 1 tail. It didn't give me an F value for 2 tail, did it? That's not even. So I'm going to ask the same question. Reject the null hypothesis or keep the null hypothesis? The null hypothesis is that there's no difference. I wanted to know if the new drill was smaller than the old drill, less variance. It's a left tail test. Does the new drill show a smaller variance? Yes or no? Why not? How can I tell? That's actually just looking at the raw data. Is it statistically significant? I need to look at these pieces of data. There are 2 different ways to tell in those 3 highlighted rows. I can look at the F calculated versus the F critical. What's my calculated F value? Say again? 0.10, 0.10. Wait a minute. What's my critical value? So 0.10 is smaller than 0.35. If I'm doing a left tail test because I wanted to know if variance 1 was smaller, is it smaller? I'm in my rejection region. I'm in the shaded area here over on the left side. I should reject. What's the other way to tell? The P. Exactly. This p-value is 0.0003. That's way smaller than 0.05, right? So the new drill is less wobbly than the old one. There's less variation. These numbers are closer together. We get better quality control from the new drill. Now, comparing those 2 original variances up there, if I look at this row, my brain goes, oh my God, the new drill is 10 times less variance. 0.00003 versus 0.00003, right? 1 more 0. 10 to the negative 6 versus 10 to the negative 5. That's much smaller. That's 10 times less wobble. Would you replace this drill? Yeah, I think it was a good idea to replace this drill. Question. How much did it cost to replace this drill? Okay. There's a difference now between a statistically significant result and a practically significant result. If this drill cost me $25 to buy a new drill bit and an hour of downtime to put it in, line it up, and calibrate the machine, I'd spend that in a heartbeat. If it cost me $25,000 and took 2 days of downtime to calibrate this machine, that might be a lot more expensive of a proposition. But if I'm drilling holes in sheet metal, I don't know what we're doing it for. So it could be I'm punching holes for IKEA parts for you guys to build shelving units at home. Do I care about the difference that much? No. On the other hand, if I'm cutting holes in sheet metal to build tanks, airplane fuselages, or rockets, I might care a lot more about how much wobble there is in that plate. I don't want another Delta jet to blow out a door panel because the screws got loose. Is it important versus is it statistically significant? Is a business decision, one you may have to make. It may not be about drilling holes in sheet metal. It may be about the effectiveness of a new advertising campaign, or the validity or utility of a membership card that tracks your purchases and offers you coupons. You know, your Advantage card at Giant Eagle or whatever grocery store you choose. Right? We got this information. Are we making good use of it? Once I know whether or not the variances are different, that can help me do the testing for means and proportions, because it allows me to pick which of the two I do, which of the two types of tests I want to engage in. So sometimes we do this test first and then do the tests for means, because it gives us which one should we do. This ends chapter 10. So chapters 8, 9, and 10 are all about confidence intervals, hypothesis testing, 1 sample and 2 sample. That's a lot of stuff. This is a good place for an exam. So the homework for this chapter is due 2 class periods from now. That's Monday. The exam will be Wednesday. On our Canvas pages and about, you get another formula sheet. You should write it up. You should be writing it now. You should write it while you do the homework. Go back and look at the last 2 chapters. Write down any formula you want to use. I will see you all on Friday, where we'll start talking more about variance, because there's a lot more to variance that I want to investigate.